Welcome to the paint shop. On today's work order, a pair of full-sized jet airplanes. Obviously no ordinary paint shop. It's Goodrich Aviation's paint hangar near Seattle. The most pressing projects today are a 737 passenger aircraft and this 757, a courier plane for UPS, which will be decked out in gold, white, and of course, brown.
We're going to use about 20 gallons of primer, about 30 gallons of white, about 30 gallons of gray, and about 20 gallons of brown. Total weight, if you put that on a pallet and in liquid form, it would weigh several thousand pounds. You would have to use a forklift to move it around.
The aircraft has already been stripped of its old paint, given a chemical conversion coating, sprayed with anti-corrosive epoxy primer, cleaned, sanded, and prepped.
It's already had the acid etch, the conversion coating, and the epoxy primer. Last night, we painted the white top coat on the aircraft, the decorative top coat. We're in process right now, as you can see, of masking off the lines and prepping for the brown.
Airplane paint must be mixed and remixed with various drying solvents and catalysts until it reaches the perfect consistency. The crew wastes no time in getting it into 5-gallon pressure pots. And the electrostatic spray guns.
Electrostatic means that there is a rounded charge to the aircraft, and the gun has a generator inside the gun that produces a positive charge. It allows the paint to transfer to the aircraft instead of overspray going all over everything that's around you.
An aircraft's paint job is critical. Without it, the aluminum airframe would be a sitting duck for the ravages of the atmosphere at 30,000 feet and 500 miles per hour.
This airplane is in 40 below zero weather at one moment, and in 15 minutes, it's on the ground in Phoenix at 115 degrees sitting on the ramp.
But like all paint jobs, this one is also intended to look good.
What we always say in the painter trade is that the first 2 coats are for dough and the third is for show.
While paint is often the last step in projects large and small, it's hardly an afterthought. Paint is big science.
The standard monomer that we use are acrylic based, and their basic structure is this.
And big business. The paint industry, known in the trade as the coatings industry, is a $70 billion per year market. The world, in case you haven't noticed, is painted. From the lines in the road and the cables that hold it up to the lines on a canvas, on the sea and in the air, on and in virtually every consumer product, and in hundreds of specialized products such as primers, lacquers, varnishes, aerosols, even electroplated industrial coatings. Paint is broadly defined as a pigmented liquid that dries to form a solid protective film. It's this transformation from liquid to solid that makes paint easy to apply and, ideally, hard to remove. There are 3 basic components to paint.
You have resin, which is kind of the binder or the glue that holds everything together when it's finally cured. You have pigment, which is the colorant, and you have some kind of solvent, which helps paint flow or smooth out as you apply it.
Pigments, which are always solid, can be anything from ground-up minerals to complex carbon-based chemicals called organic pigments. The binder or resin can be anything from linseed oil to lengthy chains of acrylic polymers. And solvents can be volatile spirits or simply water. Modern chemistry aside, the basics of paint go back 30,000 years to the limestone hills of southern France. In the beginning, there was paint. Inside the caves of Chauvet, France, are the earliest known examples of human beings painting the walls of their homes. These well-rendered hunting scenes from 34,000 years ago display considerable artistic skill, but also a keen eye for creating pigments.
They used what was available, and they turned around and they saw little lumps of red rock around them, so they ground that up to make red pigment.
Near Chauvet and other prehistoric caves, the earth also yielded yellow and rust-colored ochres.
And then they also were familiar, of course, with chalk, because that was naturally occurring, and they were familiar with black, because they got that from charcoal. And that's what their pigment range was. It was black, white, red, yellow, orange.
These earth pigments, often mixed with a binder of animal fat to adhere to the cave wall, are still a common source of color today.
They are extremely stable. You dig them up out of the ground, they're stable over geologic time. Their color is not going to drift.
The first major advances in paint technology came from the Egyptians, who placed tremendous symbolic value on vivid colors. One of these was the first synthetic pigment, Egyptian blue. This rare blue pigment, as vibrant today as the day it was painted, seems to have emerged from the glassmaking process.
And it's not known, of course, how they discovered Egyptian blue, but the general supposition is that some batch of material they were using, most likely sand, contained a little cobalt pigment or copper pigment, and the glass that they made turned out to be blue. And they must have been amazed at this, and they used this as a pigment. They grind it up and suspend it as a very fine powder.
The Egyptians also devised an ingenious method to make white and red pigments from lead. In mounds of fermenting animal dung, dual-compartment clay pots were filled with lead strips and vinegar. The vinegar fumes and animal dung combined to turn the lead into lead carbonate, thus making the metal white. The lead white was then ground into a powder and suspended in a binder of animal glue or egg white. Egyptian tomb paintings began as raised figures meticulously carved out of stone. These were coated with glue-like preparations known as gesso or size, over which the painters added the colors. In the classical world, pigments were still hard to come by, but Greece and Rome were hardly the white marble worlds we often imagine. Statues and even large public buildings were most likely brightly painted.
And the Roman wall paintings were stunning. If you go to Pompeii, where miraculously they have been preserved, and now they've been excavated from the volcanic ash, you find the most amazing walls of vermilion, which are some of the most colorful things we have till today.
Medieval alchemists perfected synthetic vermilion by combining mercury and sulfur. It became the most prized red pigment of the Middle Ages and Renaissance. But medieval paint still relied heavily on pigments straight out of the ground. Some came at great cost. A good blue required grinding the precious gemstone, lapis lazuli, and turning it into equally precious ultramarine. The most common binder used during the Middle Ages was tempera, a mixture of water and egg yolk.
They would take the pigments and grind them into the egg yolk, and anyone who's ever had their car egged knows how strong a binder egg is. And so it worked very well. Those paintings are still very, very beautiful.
Paint on buildings was most often thickened with lime. Lime is calcium carbonate powder, taken from limestone, heated in a kiln, and slaked with water. It makes a good paint for masonry buildings because it allows the stones to breathe. Lime paint was therefore the coating of choice for castles. But it would take a revolution in science and a renaissance in technique to bring paint into the castle that is every man's and woman's home. Today's paint store offers a universe of color choices unknown to thousands of generations of human beings. Customers who bring in a paint swatch walk away with a gallon of precisely color-matched paint in minutes. Using 12 highly concentrated pigment mixtures called colorants, a paint retailer, with a little help from the computer, dispenses the exact combination of color into the base paint. Out of these colors comes an infinite palette.
This is our Flowmaster tint machine. This is what we make all our colors from. This is all the equipment, machinery that makes it all happen. You've got circuit boards. You've got 12 circuit boards, one for each color.
Benjamin Moore pioneered custom color matching in 1983 by developing a system that uses a spectrophotometer along with a computer to calculate how to match any color. So literally a customer can bring in a color swatch, show it to the spectrophotometer, do some computing, and what will come out is a formula that tells the retailer exactly how to make that color.
In the age of computer-matched, shaken-to-order colors, it's easy to forget the hundreds of years of innovation that led us here. Using a centuries-old method to transform powder into paint, Robert Gamblin demonstrates some of the key building blocks. One of them is a viscous transparent liquid that changed the history of paint: linseed oil.
The flax plant is where linseed oil comes from. The flax plant has meant so much to oil painting because most of the canvases for hundreds of years were woven out of the stalk of the flax plant, and the seeds, which can be crushed, and about half of the weight of that seed can be expressed as oil. Maybe 90% of the weight of that actual piece of art came from the flax plant. I can hear little pops as I do this, and with every one of those little pops, I'm taking an agglomerate of pigment and I am separating them down. This paint is starting to look very good. It's starting to get very nice and glossy, which is telling me that I have a nice ratio of oil to pigment.
Although scattered evidence of oil painting dates back to antiquity, it was the 15th century Flemish master, Jan van Eyck, who brilliantly demonstrated what oil paint could do.
There are many scientific features about oil painting which give the painting an entirely different aspect than what you get from tempera painting. For example, the light comes and bounces off the smooth surface as it does off a mirror. And the light goes into the oil layer, the dried oil, and the optics of it such that ray of light is focused back and forth, so it passes through pigment particles held in that oil layer many times. And therefore, the color associated with those pigment particles is accentuated by the many transits that the light makes.
Luminous linseed oil paint fueled the glory of the Renaissance, and it quickly replaced tempera as the dominant binder in artists' paints. But pigment technology didn't undergo a similar breakthrough until the birth of modern chemistry and the fires of the Industrial Revolution.
Firstly was the development of electricity. So you could use electricity to take chemical compounds and reduce them down to their elements, particular things like sodium and potassium. And once you got these very reactive sodium and potassium produced by electrolysis, then you could use those elements to reduce any other chemical compound that you might find.
As chemists began isolating pure elements at the turn of the 19th century, metallurgists took the knowledge and began fusing metals together.
You put these materials essentially side by side, ground up very fine, and you put them in an oven at 2,000 degrees, and after 8 to 10 hours, close to the surface of the sun, these metals fuse together.
It so happened that a number of these compounds were colored.
As the 19th century progressed, the wonders of chemistry would reach their full flowering with the Impressionists, who hungrily absorbed the modern colors into their groundbreaking art.
My favorite picture demonstrating this is a painting by Renoir. The River Seine, which is blue, obviously is made from cobalt blue. And the orange skiff is made from chrome orange. And those two dominant features in the painting were the new pigments, and that picture could really not have been painted before that period.
In fact, we think that the Impressionist paintings are as much a product of the Industrial Revolution as the steam engine is.
These cobalts and cadmiums and chromiums were also the first industrial paints.
This is the first time that it was possible to paint almost anything you wanted, a house, a carriage, because industry created the capacity to produce huge amounts of pigments, huge amounts of binders, then made it possible to build your house out of wood and protect that wood with paint.
Before the 19th century, paints on houses had been used sparingly.
And the earlier you go, the fewer houses were painted. In the early days of New England, for example, you would paint the trim and the windows typically in a house. But even into the 19th century, you would see towns in which many houses may not have been painted at all.
Such is the case at the Fairbanks House. Built in 1636, it's the oldest surviving timber frame house in North America.
The very earliest surfaces at the Fairbanks House had no paints on them whatsoever. As we move through the 17th century and into the 18th century, there's a period where they're relying on whitewashes.
Whitewash is a type of lime-based paint, but it's a poor fit for wooden surfaces. The expansion and contraction of the wood pushes off the paint. At least one vital structure was often painted: the barn. Most farmers used red ferrous oxide pigment. It's a poison to damaging moss and mold. Painting one's own house remained beyond the reach of most people. But with readily available ingredients, improved transportation, and the invention of the resealable paint can in 1879, house paint companies began to proliferate. Meanwhile, as the 19th century came to a close, industry began to find uses for a different kind of oil. Organic chemists learned to produce vivid petroleum-based pigments.
Now, it's organic in the sense that these are carbon-based compounds. The source of that carbon is petroleum.
The same hydrocarbons that accelerated the pace of technology could be rearranged in the lab to form intensely bright synthetic colors.
When you think about color, most of the color that we see, most of the really rich, beautiful color that we see, is coming from organic pigments or organic chemistry pigments.
By the 1920s, organic chemistry had also led to new ways of formulating paint binders. Fast-drying nitrocellulose lacquer was synthesized in 1922 and was immediately put to use by time-conscious Henry Ford. Before, automakers had used mainly hand-brush varnishes that took up to a month to dry. Organic binders called alkyds, essentially synthetic oil paints, kicked off a century of research into ever-stronger paint films. And two giant innovations would finally make painting a do-it-yourself job. This is truly the golden age for do-it-yourself painting. To understand how we got here, we have to pop open the lid and examine two key ingredients. The first is a humble white pigment known as titanium dioxide, the unsung hero in the history of paint.
Titanium dioxide is really critical to making modern paints. It's what makes the paint hide the surface. On a functional level, what titanium does is it blocks ultraviolet light, sunlight, from penetrating the paint to the surface beneath, and so it provides protection for the surface.
In fact, TiO2 is so effective at blocking damaging light, and so safe, that it's used in sunscreen. Before TiO2 came along, artists and house painters alike relied on one main source for white pigment: lead. The heavy metal makes an excellent white, but its toxicity was recognized by the 1950s.
Lead poisoning of young children is a very serious problem. Lead is a neurotoxin. It affects the nervous system and is particularly serious for very young children.
And it was banned in 1978. Titanium is not only safe, it's abundant. Like all mineral pigments, it worked its way into the paint store from the ground up.
TiO2, titanium.
This floating dredge operation in Florida extracts 30,000 gallons of water and sand per minute.
Right now, I've got on the line approximately 2,300 tons. We chew up the base of the bank with a cutter head, and we got a big suction pipe. The pump sucks the sand through the suction and pumps it over to our wet mill.
The mill sifts out the titanium, which is only 2% of the material. At a plant operated by DuPont, the world's largest titanium dioxide producer, the TiO2 is cooked in gigantic furnaces. The extreme heat and a chlorination process turn the metal white. In this case, it emerges as a thick white slurry. A major destination for TiO2, places like the Benjamin Moore Paint Factory in Newark, New Jersey.
A facility like this can make about 50,000 gallons maximum in one day.
It all begins when these 2,000-pound sacks of dry titanium dioxide are mixed into an agitator tank with a number of dry and wet ingredients. The most important wet ingredients are water and a second breakthrough paint technology, latex resin.
The latex paint was really a huge innovation that occurred largely after World War II. Latex probably came out of the search for a synthetic rubber. And during World War II, they were working with materials like styrene butadiene to make synthetic rubber. They made this in water system so that it was an emulsion. And they realized they could actually form a film with this. And therefore, it evolved into what we now have as latex paints.
I think the invention of latex paint was probably the single most important breakthrough in the history of paint, even. Prior to that, the kind of paints that we used were solvent-based paints, alkyds typically, that contained a lot of hydrocarbon solvents like mineral spirits. And although these paints work quite well and are still used today, there were hazards of flammability, there were considerable odor problems. Most people probably know these paints take quite a long time to dry.
First sold in 1947, latex launched the post-war do-it-yourself painting movement. Latex resins are composed of petroleum-derived monomers formed into polymers in a water dispersion.
Latex paint dries by the evaporation of water and then the coalescing of the individual latex particles. As the water evaporates, they move closer and closer together, and when they find each other, so to speak, they merge or fuse into a coherent film.
Back at the Newark plant, the TiO2, water, and latex resin are becoming one.
This is a 10,000-gallon holding tank. The paint that we mixed earlier, we pumped it in here. We added the titanium dioxide slurry. We added latex, some other ingredients to finish the paint off. This agitator will keep it mixing while we do the quality check.
After being strained, a product that can now officially be called paint flows down into the filling lines, where it's sealed in 1-gallon cans. A much more colorful operation is taking place in this room, where Benjamin Moore manufactures its own colorants. Deep iron oxides and vivid synthetics are mixed in 12 color-coded vats, which happen to match precisely the 12 computer-controlled canisters back at the retail store. Today is Magenta Day. After an initial mix, the pigment particles must be broken down further to maximize their color.
So what we're doing, we're pumping out of this tank through this pipe right here, up into this chamber. Now inside this chamber, there's a big shaft that's spinning, and there are a number of these agitators inside there that are spinning around very fast. There are also in that chamber these beads, and these are high-density ceramic beads, and they are smashing against those pigment particles, breaking them down. If we don't break those pigment particles down, we don't get the color efficiency. So we use the mill to extract all of the power out of that magenta pigment.
Each colorant flows into one of 12 pipes and into a can. Once shipped to the retail stores, these highly concentrated, much smaller cans will provide the punch needed to turn millions of gallons of titanium dioxide white paint into infinitely colored living rooms, bedrooms, and offices. House paints are the largest segment of the coatings market, in part because it's become so easy to buy and apply ready-made paint. Other paint jobs remain difficult. But in the high-tech world of automotive and industrial coatings, the results can be spectacular. One of the military's best-kept secrets is a paint. Namely, the cloaking technology in the black paint of the stealth bomber, which prevents the reflection of radar waves. While not all paint is quite so secret, the world of industrial, automotive, and aviation coatings is largely hidden. And yet, its results are everywhere. Wherever there's key infrastructure, there's industrial paint, protecting bridges and roadways, airplanes and ships, pipelines and storage tanks. Their common enemy? Corrosion.
A corrosion reaction is essentially an electrochemical reaction between two materials.
The most widespread reaction is when the iron in a steel structure is turned into iron oxide, or rust, by water, salt, and ultraviolet radiation. The electrochemical reaction between the iron and the various elements causes electrons in the structure to flee, not unlike a battery draining. A zinc-rich pigment is often the solution for protecting steel,
We put materials into the coating that will restrict the flow of electrons so that battery can't operate and therefore the material can't corrode.
Creating a paint that will protect an automobile is one of the greatest challenges for the coatings industry. After all, what other consumer paint job must resist sun, ice, rain, gravel, and abrasion for a decade or more? Retain its resale value and look cool while doing it.
The paint finish and the color really have to survive a lot. And so we use what we call high-performance pigments. And high performance really means that they're pigments that are designed to be durable over many years.
At BASF's Detroit Research Facility, creating a beautiful paint job that will last is an obsession. Paint samples here undergo punishing tests. They experience wet, salty weather conditions in weatherometers and are pummeled by gravel in, you guessed it, gravelometers. UV chambers simulate months of harsh sunlight. All the while, scientists and a very expensive robot analyze each paint's durability and color fastness.
I don't know if people realize that the thickness of their paint on the car is really only about as thick as a sheet of paper. And that thickness needs to provide all that protection for that car and keep it shiny and the customer happy for 10 years.
Along the assembly lines of automakers, creating this paper-thin armor begins with a phosphate conversion coating. The metal substrate is chemically altered to make it more adherent to the coming layers of primer and paint.
The first primer is an electrodeposition primer, commonly called electrocoat. And in that coating, the car body is actually dipped into a huge tank, about the size of a swimming pool, actually.
It's called electrocoat because while in the primer bath, the car body is given a negative charge. The positively charged primer particles flow onto the car's surface, where they stick. Then the primer is baked on, triggering a crucial chemical reaction known as cross-linking.
Cross-linking is a reaction between two different polymer strands, if you will. And what happens is you build up a polymeric superstructure, a bigger molecule, and these can be linear or they can actually be branched into 3 dimensions. And one way to catalyze those reactions, to get this chemistry going, this bond breaking and bond formation, is to put energy into the system. And one way to put energy into the system is to raise the temperature.
The next step would be to go to a spray prime, which probably has some color, and the car would move on to a base coat color. And that's really where the color comes from.
At this point, the car's distinctive clear coat is also sprayed on.
In essence, clear coat is the resin component. It gives the color a little bit more depth, and it's become the standard of the industry, really, so that when people see a car, they really think that it should have that wet look, that clear-coated look, and that's what clear coat does.
Since the 1950s, automotive paints have largely moved from alkyd resins to acrylics, basically a form of latex. In so doing, car paint makers have greatly reduced the amount of VOCs, volatile organic compounds, in the solvent. When VOCs evaporate, they bond with nitrous oxides in the atmosphere to form smog. Today, the most common solvent is water.
If you look back to when paints were first used, when Henry Ford was painting cars on his assembly line, he was probably using a paint that had 20% solid paint in it and about 80% solvent. And that trend has been changed, and now We're making paints, in the case of the electrodeposition primer, you have 1% solvent or less in that.
Though less glamorous than the sheen of a sports car, other industrial coatings are just as important in sustaining a high-tech world.
People may not realize that a lot of the modern electronic equipment that's largely made out of plastics has to be painted because they have a lot of delicate circuitry inside. And this could be driven haywire, in essence, by extraneous electromagnetic radiation. We have a whole class of coatings. They're called EMI, RFI shielding coatings. And that stands for electromagnetic interference and radio frequency interference. And these paints contain a large amount of metal. The solution is you paint the plastic with a paint that simulates the function of the metal.
Paint's protective coating helps keep products lightweight and affordable. Stoves need paints that are heat resistant. Metal-clad buildings need coatings to battle against UV damage. Even welding steel can be given a coating that conducts electricity. And in the ultimate tribute to the ubiquity of paint, industrial coatings are even used to paint the inside of paint cans. Since paint is everywhere, its chemical makeup must be closely regulated. Today's scientists are constantly striving to reduce paint's environmental footprint, even as the technology heads into outer space. As on Earth, the main job of paint in space is to protect a valuable object from the elements. Paint serves a critical function in extending the mission life of space stations, orbiting telescopes, and most importantly for 21st century Earthlings, satellites.
Okay, you ready?
Here at Wright-Patterson Air Force Base, paint samples are zapped with UV radiation equivalent to that found in space, and blasts from proton and electron guns to make sure they're up to the task.
The job of the coatings on a satellite is designed to help control the temperature of the electronics. The electronics are generating a lot of power, they generate a lot of waste heat, and we need to be able to get rid of that heat by wicking it out to the exteriors of the satellite.
On the exterior of a spacecraft, white painted surfaces are designed to reflect the intense UV solar radiation. Most satellites use a form of zinc oxide coating, an earth pigment not terribly unlike those used by the very first painters.
The paint also has to be semiconductive. It has to be able to conduct electricity to some degree, otherwise it's going to build up a static charge. And the charges can be fairly large, which can create failures and can bring your satellite to its knees.
Thanks in no small measure to space-age coatings, that is a rare occurrence. Back on Earth, the future of paint is also bright. Chemists continue to reduce the environmental impact of paint, while making it ever more durable and colorful.
It's one of the things that spurs a technological advancement within the industry. You remove a lead, you remove a mercury, you've got to replace it with something. And oftentimes the replacements are superior. Without regulations, I may not even have a job.
The primary concern today continues to be the element of paint that vanishes as soon as the paint dries: the solvent.
The solvent portion of paints is compelling to me. It's really the part of the paint that's fugitive. It's in the wet product, but it's not in the dry product. So it's going to evaporate.
The need for volatile solvents, those composed of liquids other than water, continues to decrease with the help of advanced technologies, like powder coatings. These tiny solid particles of paint contain no solvent at all. They're sprayed onto the substrate and heated to a liquid, which then hardens. A traditional enemy of paint, UV light, is used to flash cure paint, like these samples, reducing the need for volatile drying solvents. Chemists are also tapping into literally green sources for the resin portion of paints.
Now what we have over here is probably what you consider the next generation of coating technologies. This product in here is a synthetic resin that had its basis as a biomass, meaning that just 2 years ago, this material in here was a plant. Benefit of that is for every pound of this resin you use, you take out about 2.5 to 3 pounds of CO2 from the atmosphere. We reduced by an order of 10 the amount of volatile organic components. That's the pollution part of a coating that goes into the atmosphere. Finally, the nice thing about this is that it's the backbone of it is extremely durable. So it actually gives you better quality performance.
There's still much work to be done in making paint a 100% clean technology. But the story of paint is far from over. The future, you could say, is a blank canvas.
There's talk of putting microprocessors into paint films, where these microprocessors in the paint are continuously informing, say, the bridge engineers as to what the wind shear is that the bridge is being exposed to.
There has been some development of paints that can heal themselves, essentially using an encapsulation technology where you have small amounts of material in the paint that when the paint is ruptured, it releases a material which will move to the ruptured area.
The Air Force has developed paints that change color in response to varying pressure levels during wind tunnel testing. And scientists at the University of Rhode Island have devised paints that change color to warn of dangerous overheating. No matter where paint takes us, it will go on making the world more colorful than our artistic ancestors could have dreamed. Meanwhile, the science behind paint will continue to evolve as quality-obsessed chemists and colorists try to make it better with each batch.
You know, I talk to people and I say, I actually enjoy watching paint dry. I really do. I do it right here in this lab all the time. And you can see me actually standing there watching paint dry because it fascinates me.